So, we have been discussing about the trajectory transfer. So, coplanar maneuver we were working out. So, and one tangent burn we have started. So, we will complete it today. So, we had one outer orbit in which the satellite was at this point, and there was an inner orbit, and then after giving one tangent burn at this place delta V A, it was brought to this place, and then another burn was given here in this place. So, this is V B in elliptical orbit, we show it by E. So, R I is the initial radius and R F is the final radius, and the true anomaly of this point was written as theta trans. Okay, and then we developed the equations which were cos theta trans of the transfer orbit at the point B. So, the subscript B is appearing. So, here the minus sign is for periapsis and plus sign for apoapsis. So, if you start here in this point, then you take the plus sign. If you start here in this point, then you take the negative sign. Okay, and n is written as R F by R I. So, using this information we calculated the E transfer orbit, eccentricity of the transfer orbit, and next we computed also semi measure of the transfer orbit. So, this was given by R initial So, in reality we will be given with two orbits, either it may be circular or it may be elliptical, okay, and the true anomaly will be given. Initial position of the satellite will be available to you. So, this is the R initial position from here to here, this is R initial, and of course, this radius of this circle, if it is a circle the final orbit, then this is given as R final. Okay, and thereafter after doing this, we can work out rest of the things. So, the steps involved So, these are the quantities given. So, from here you have to determine eccentricity of the transfer orbit, A transfer orbit, and the time for transferring from A to B, and of course, delta V A and delta V B, the impulses required at the 2 points A and B. So, this is point B and this is point A. So, here the how much impulse is required, this will be denoted by delta V and this is delta V A. Okay, and we have put there, we can remove the sign just V R because we are showing it in this direction. So, no need of showing the sign. Basically, we need to deboost in this place and again here we have to bring it in the smaller orbit. So, we need to deboost it. Okay, so, here this is the VBC, the velocity at point B in the circular orbit, if it is a circular orbit, and this is the impulse then required to bring it to this. So, so let us compute these quantities one by one. V initial, if the outer orbit is a circular orbit. So, this will be simply written as mu by r initial under root. The next you have V final, you can write as mu by r final under root, and V in the transfer orbit at point A, this will be 2 mu by r initial minus 1 mu by A transfer orbit square root, and at point B in the transfer orbit, this is mu by r final minus mu by A trans under root. Okay, so, first you have need to compute all these quantities, then delta V B will be given as, okay, let us first compute delta V A. So, V trans A minus V initial. Similarly, delta V will be given by, now in the case of delta V B, which is shown by this small green line, here it is difficult to see it, but it is appearing something like this is V B and suppose this is V B C. So, then you need to give, this vector is larger. So, you need to give boost it here in this place. So, this will be quantity here delta V B. So, delta V B will be given by V trans B square and then V final square minus 2 V trans A V trans B times V final times cos phi at B. The phi B is the flight path angle at B. So, the total velocity change required delta V will be delta V A plus delta V B Okay, the flight path angle cos phi b, it can be written as 1 plus e cos theta divided by 1 plus 2 e cos theta plus e square under root, and sin phi b can be written as e sin theta where you can look at how we define the angles. Again I am repeating, if this is the v direction, this is the radius direction. So, this is the radius vector in this direction and this is theta direction. Okay, then this is your phi, okay, and this angle is your theta, which gives you the true anomaly. So, we are measuring from the perigee position. and tan phi b, this will be written as E sin theta by 1 plus E cos theta. So, these are the relationship that you can derive, and all these things we have worked out earlier. So, no need of repeating in this place again. Okay. Now, what you need to do here, find out the eccentric anomaly using this equation. So, look into earlier lectures, we have developed all these things. So, E trans plus cos theta trans b divided by 1 plus E trans eccentricity of the transfer orbit times cos theta transfer orbit at b, and where E is the eccentric anomaly. Okay, you need this quantity, I am going to explain. Say if you want to find out the flight time from A to B, so you need to integrate the equation which earlier we have written as r square theta dot equal to h, and this was written as dy dt equal to h by r square, and for finding out the dt, this was integrated, and this is r square by h d theta. We integrated this, and you know that while working with the Kepler's equation, so we did all these things. So, the same equation we have chosen here in this place. So, this is while working for the Kepler's equation, we derived this relationship, and the same relationship we are using here. Okay. Now, if you use the true anomaly, so finding out the time, then you need to integrate the equation. So, to avoid that, we work in terms of the eccentric anomaly. So, that flight time will be given by, now the flight time taken, that will be obviously, if we are expressing in terms of, this is an elliptical orbit, and here the angular rate is obviously varying as the r varies, and therefore, the angular rate you can see from this place, h is a constant, and therefore, as the r varies, the angular rate, the theta dot, which is, it keeps varying. So, therefore, instead of using a changing theta, which needs the integration of this equation, so we use the mean angular rate, and mean angular rate, obviously you know that for mean angular rate, this is given by mu by a q under root, okay. And from obviously from this place you can write 2 pi by t equal to mu by a q under root, and t becomes 2 pi times a q by mu under root. So, this is the time period of the satellite to complete one orbit. So, if it starts from here and if you leave here, so it will come back after this much of period, where A is the A transfer orbit, semi major axis of the transfer orbit. Now, we do not want to use this equation, particular equation given here. So, rather we will write the whole thing in the eccentric anomaly. So, tau transfer, this will be given as, now you can look from this place, this is for 2 pi period. If you have to go through 2 pi radians, then you need this much of time, which is indicated by capital T, and if you have to go by some smaller angle, say theta, so you need a smaller amount of time. So, here the theta, instead of working in terms of theta, we are just indicating using this mean angular rate, which is given by mu by a q. So, here this will become a q by mu under root times. Now, suppose you let the satellite go again and again in this orbit, it is going from here to here, passing here, coming here. So, it may go k times, and after that you are carrying out the maneuver. So, So, you need to include all those angles here. So, this can be written as 2 k pi, this is for the repetition, how many times you are repeating that orbit, plus E minus E trans sin E minus E 0 . So, this is the eccentric anomaly of this point, and this is the eccentric anomaly from where you are starting this point. So, we are starting here in this point, and this is your elliptical orbit which is getting completed like this. Okay. So, eccentric anomaly of this point, and what is the eccentric anomaly of this point? So, you have to subtract like this, and this quantity is nothing but we are writing in terms of the eccentric anomaly. So, this is nothing but your mean anomaly. So, mean anomaly of point B, and this is mean anomaly of point A. Okay. So, this gives you the transfer time which is required if k equal to 0, means in the first shot only you are going to transfer it. So, k will be equal to 0 and only these quantities are required. Okay. Now, we have done this. So, for last time problem which we left out. So, what we need to do now is to complete that. Okay. And before completing that, the equations that I have used, I will just work it out for you. This cos phi and sin phi, it is easy to see that if this angle is theta and this angle is phi, and earlier we defined this angle, if you look into earlier lecture. So, we defined this as angle as alpha. Okay. So, either we can define this angle as alpha, or either I can define the angle from here to here as alpha, and depending on the how you are defining this angle alpha, the equations for tan alpha changes. So, if you define tan alpha from here to here, so this becomes tan alpha equal to minus E sin theta by 1 plus E cos theta, and this we have worked out earlier. Okay. Thus, but we worked out by writing here alpha from this place to this place. Now, we have shown the alpha from here to here. If you want to do other way, so what you need to do, if you indicate alpha say from here to here. So, let us say this quantity is alpha 0 you are writing. So, tan alpha 0 you want to indicate in terms of tan alpha 0. So, the same here, if alpha will become alpha 0 plus pi by 2. Okay, and this is the quantity on the right hand side. So, this quantity becomes cot Okay. So, either you express it in this way. So, from here you can get the value of alpha 0, or either you express it in this way, both are possible. So, if we take this option, then we have the working out for phi here. So, we can directly write phi equal to tan phi equal to tan 180 degree minus alpha, and this becomes tan minus tan alpha. So, this minus tan alpha you can put from this place. So, this is E sin theta by 1 plus E cos theta, and this is what we are interested in, and where phi is the flight path angle. This is FPA, flight path angle. Okay, once this is known to you, then sin phi simply you can write as sin phi by cos phi times cos phi. So, this becomes tan phi divided by sec phi 1 plus tan square phi under root, and insert the value for tan phi here, and the value for the sin phi you get as E sin theta divided by 1 plus 2 E cos theta plus C square under root, and similarly cos phi you can get as 1 plus E cos theta divided by 1 plus 2 E cos theta plus C square under root. Okay, it is easy working out. You just look into other lectures and you can complete it. Okay, now we complete the last time problem. The last time we left it because this problem was bit lengthy and I did not want to cover it in this one go. So, the problem given was the first part we were working out, that we have two heliocentric orbits in which one asteroid was at the point A, another asteroid was at point B. Where this angle was say the theta A. So, theta A was given to be 139 degree, and the angle from here to here. So, this angle was theta B, and theta B was given to be 271 degree. Now, the problem was that some satellite is to be launched from A, okay, and A is moving, B is also moving, and this satellite has to catch up B. So, the requirement was also that we have to do the Hohmann transfer. Hohmann transfer for fuel efficiency or saving the propellant. Okay, and obviously, in this case R final was given to be 3.5 astronomical unit and R initial was given to be 2 astronomical units, and therefore, R f by R I, this is 3.5 divided by 2, and this is less than 11.94, and therefore, Hohmann transfer can be applied, okay, and it will be fuel efficient. But before catching this, so Hohmann transfer can be applied such that if you are suppose you are applying the Hohmann transfer in this place. So, at that time while the satellite is catching B, so B must come out to be here in this point. So, exactly the pi degree pi radians the satellite has to move from this point to this point. So, this point we termed as A1, okay, from where, and this angle we wrote as delta theta A, and then the satellite was launched from here to here, and it went and caught up the asteroid B at the point B prime. So, in the first go, what we have worked out, that theta A plus delta theta A plus the angle from here to here, which is nothing but pi, this should be equal to the angle which B will move from here to here, that it will cover. So, that was delta theta B plus theta B. So, this angle from here to here and then from here to this place, and from this place to this place, this is total angle here, and from here to here this is angle your theta b, and from this place to this place this is, so we can show it here, this angle is from this place to this place, this angle is your delta theta b. So, this must equalize, obviously it is apparent from our figure. Okay, because it is a Hohmann transfer, and in this transfer orbit we are boosting at the point A1. So, this is basically you are doing the firing the rocket at the perigee of this transfer orbit, and this is the opposite point of the transfer orbit. So, the semi major axis x was given by r initial plus r final divided by 2. So, this was 2 plus 3.5 divided by 2 astronomical units. So, this 2.75 astronomical unit. This we calculated last time. And then using various relationship, then we worked out omega a also. So, omega a turned out to be 7.0393902 into 10 to the power minus 8 radians per second, and omega b similarly we calculated to be 3.0407308 into 10 to the power minus 8 radian per second. Now, the time of flight for completing this orbit from here to here. So, this is half the orbit. So, will we say this is T 1 by 2, this is nothing but pi times 2.75 astronomical unit, it is in astronomical unit. So, this we can write as r. So, where r equal to 1 astronomical unit, okay, divided by mu and this whole cube under root. So, this is the half time period, and if we put 2 pi, means that will be time to start from here to here for the satellite and come back again to this point. And putting the relevant values, then we calculated. So, put the value for the r. So, last time we have stated the value of r. So, r was having a value of r equal to 1.49596 into 10 to the power 8 kilometers. So, this is 1 astronomical unit. Okay. And similarly, mu, the value for the mu that we chose, it was 1.32715 into 10 to the power 11 kilometer cubic per second square. Okay. So, this with these values inserting into this gives you 719,56309 seconds. And if you convert this into day, so in day this will turn out to be 832.82765 days. So, we divide it by 719,56309 and divide by 24 times 3600. So, this will give you this value. This is 719. Okay, and then we also calculated delta theta a by omega a, which is equal to T a delta T a. So, delta T a is nothing but the time taken for the asteroid to move from this point to this point. Okay. And this is what was asked in the question, that how much time is required before the satellite can be launched from the asteroid A. Okay. So, this is the time, this is the angle before you can launch, and if you divide by the angular rate of the asteroid. So, that gives you the time. So, this is what exactly has been done. So, this is the waiting period before you can launch the satellite, and this turned out to be 3376.7308 seconds, which was equal to 390.8253 days. So, this was the waiting period. Delta T a is the waiting period before you can launch satellite from asteroid A to have maximum fuel efficiency. So, if you have to send your satellite from Earth to Mars, so you have to follow exactly the same pattern. Here you need to know the initial position of the Earth, initial position of the Mars at a particular epoch from where you are counting, and then you have to compute when your window is available for launching the satellite. Okay. So, that window you have to calculate exactly in the same way, and then you can prepare the mission for sending your satellite to Mars. Okay. Now, by how much angle the asteroid will move from this epoch. So, this is our starting epoch, okay. And from here how much angle it is going to describe. So, the asteroid A is already here in this position, it is moving to this position, and then it is launching the satellite. So, in the meanwhile asteroid A will move from position A to, suppose it is moving and reaching this position A prime. Okay, while the satellite catches up at B prime. So, asteroid has moved to A prime, which is the position given here. So, A prime will be the delta theta A prime, this will be equal to theta A plus delta theta A plus. So, you have the angle theta A from here to here, and this is the angle delta theta A, and the rest of the angle from here to here to this place. Okay. Now, this depends on the angular velocity of the asteroid and the time taken in the meanwhile, how much time the satellite takes from here to here. Okay. In the meanwhile, the asteroid B is reaching from this place to this place, and that will be given by the half period of the elliptical orbit. So, this is 2.75 times r to the power 3 by 2 times omega a. Now, insert the values for all of them and you can calculate. So, delta theta a we have already found out, delta theta a was we can write it here, omega a times delta T a. So, delta T a is the time that we have just now calculated. This is the quantity here delta T A 390 days. Okay, and second it is given like this, and delta theta A also was available to us. Okay, anyway, we will write here. This is omega A is 7.0393902 into 10 to the power minus 8 times. This is the angular velocity and times delta T. So, delta T is your delta T A. This is 33767308. This is the in seconds. This is what the quantity is shown. So, we have taken here in this place. Okay. So, this turns out to be 2.37700126 radians. Okay. Similarly, this quantity you can compute, and this quantity pi by mu under root times 2.75 r to the power 3 by 2 times omega A. So, inserting all the values, r is the one astronomical unit and omega is the angular speed which is shown here. So, inserting these values, pi you know and mu earlier we have stated. This is the gravitational constant of sun. This is not the universal gravitational constant, this is the gravitational constant of sun, as in the earlier lecture we have discussed. So, by inserting all the values, this will turn out to be, so omega A is 7.30 7.0393902 into 10 to the power minus 8, and this quantity we can compute and write here. So, this quantity is 719,56309. You can verify yourself. So, this will turn out to be 5.0652845 radians. So, therefore, theta prime A in degree, this will be given by 139 degree plus 2.37700126 plus 5.0652845 into 180 divided by pi. So, 139 degree plus 426.41227. Each of the computation you must verify yourself if you want to learn. Okay, and this is 565.41227 degree. This is what is coming. So, around 565.41 degree. Okay, similarly, we have to calculate the position of the asteroid B. So, new position of the asteroid B which is B prime. So, theta B prime, this will be theta B plus omega B times delta T A plus omega B times pi by under root 2 mu 2.75 r to the power 3 by 2. So, you can look what are the quantities these are. Look into this figure. So, theta omega B times delta T A. So, this is the time in which the asteroid A moves from point A to A1. Okay, this is the point A1. So, it is moving from this position to this position, and that time we have written as delta T A. And this time we have earlier calculated, this is known to us, omega V is known to us, this quantity is known to us, all these quantities are known, and this is basically your flight time of the satellite. So, the satellite, the time it takes to move from here to here. So, in the same time, So, the time A takes to move to A1. So, that time B will move from here to, suppose it moves to this place, and thereafter the satellite moves from here to here. So, B will approach here in this point, and both of them will meet together here in this point B prime. So, this is what the equation appears. Now, each of the values you can compute separately. So, omega B times delta T A. I am again stating that you must do it independently by computing and verifying all the results, and that will give you confidence to work out this example. Okay. So, this is your delta T A and this is omega B. So, this will turn out to be 1.0267729 radian. Okay. This is the value. Now, we next need to compute this. So, this quantity earlier we have computed in the previous example, in the previous step. Okay, here we computed this quantity, which is appearing here in this place 719,56309. So, we can utilize here, and this has to be multiplied by omega B. So, next the quantity W B times T 1 by 2, this will be omega B times pi by mu under root times 2.75. This is the semi major axis of the transfer orbit, what we are writing here, and this is the period for completing the half orbit. Okay. So, this is your T 1 by 2. Okay. Now, inserting these values, omega B is 30407,308 into 10 to the power minus 8. Okay. And this quantity we have calculated earlier. This is nothing but 33 no, this is not the quantity. Okay, here we have done it 719,56309. 719,56309. Okay, so if you multiply this, this turns out to be 2.1879977 radian, and therefore, theta prime B, this can be written as 271 plus 1.0267729 plus 2.1879977 into 180 divided by pi. Okay, so 271 degree plus 184.19278 degree. So, this turns out to be 455.19278 degree, means 0.192 degree or 0.193 degree we can approximate. So, this is your theta prime B. So, what ultimately we have got is as the result theta prime A, this is equal to 565.41227 degree, and theta prime B equal to 455.19278 degree. Okay. Therefore, you can see from this place that asteroid A is leading in latitude. Okay. So, this quantity theta A prime minus theta prime B, this will write subtract and write this as delta theta, which will be 565.41227 degree minus 455.19278 degree, and this turns out to be 110.21949 degree. So, this is the lead available to asteroid A. Now, the part B of the question is, part A is over. So, part B of the question is that once the asteroid has reached into the point B and the satellite has caught this rendezvous has taken place. So, satellite has caught the asteroid B at B prime. Now, if the astronomer who is sitting in the satellite, if he wants to return back to A again, okay, how long he has to wait? Okay, if he wants to minimize the fuel. Okay. So, next the question is that if this satellite which has reached point B prime has to return back to asteroid A again, then how long the wait period will be? For maximum fuel economy. So, this is the second part of the question. Okay, again we draw the figure. So, with respect to asteroid B, we can show that this is the position B prime suppose, and the asteroid which is in a smaller orbit. So, this is located somewhere in this point. So, this is your A prime point. Okay. So, this is the initial situation and the lead is of the lead angle we will show it by delta theta, and delta theta just now we calculated, it turned out to be 110.21949 degree. Okay. So, how long the waiting period will be before we can launch a satellite from the asteroid which is now at B prime. So, suppose that before the launch can be done. So, this moves to some new position here B double prime. Okay. In the meanwhile, it will move into A prime will also move. Okay. So, A prime is moving, this asteroid A is also moving, asteroid B is also moving, but the thing is that we have to always launch in such a way. Now, here this will be the apogee position and then you have to cut up this at the perigee position of the this transfer orbit. Okay. So, we need to work out further this quantity. Now, let us see how to do it. So, we will write delta theta B plus 180 degree. Okay. We are writing in terms of right now in terms of degree, later on we will convert into radians. So, you see that delta theta B, this will be indicated by something like this line. This is your angle delta theta B, and then suppose it catches A at this point. So, this will be angle from here to here. Now, but this satellite asteroid A is in the smaller orbit. So, its angular rate is fast. So, by the time it goes here, so this will be covering a larger angle and it will cross it. Okay. So, it won't be possible to catch up here in this place. We will have to wait for one more period once it returns back and comes into this position. So, we have to compute for that quantity. So, this will be given by delta theta plus say the delta theta A is the angle covered by the asteroid A. Okay. So, delta theta is already the lead available and delta theta A is the another angle that it will be moving around and coming into this position, and then B will be coming and catching up here in the satellite will start from here and catch up here in this position. So, we need to subtract here 360 degree. So, because it has taken one round already here to come to this point. So, these things must be taken care of. So, if you write in this fashion, then your delta theta b, insert the value of delta theta from this place. So, delta theta b can be written as delta theta b plus 180 degree equal to delta theta 110.21949 plus delta theta a minus 360 degree, and working it out, delta theta a can be written as 429.7805 1 degree plus delta theta b. So, this time we have expressed delta theta a in terms of delta theta b. So, let us say this is our equation number A. Now, the next step will be to compute the time taken. So, to cover this angle, the total time required, and to cover this angle, the total time required, they must be same. So, let us convert this into the radians. So, if we convert this into radians, so delta theta a can be written as in radians 429.7805 1 degree into pi by 180 plus delta theta b, where delta theta a and delta theta b are now in radian. Okay, so, this becomes 7.501085 plus delta theta b. Okay. Now, we can go for calculating the equating the time. So, now delta theta a divided by a will move from this place and it goes once around this and whatever happens to this. So, we have the time delta theta a by omega a, this must be equal to delta t 1 by 2 is this is the flight period. Okay, so, we will continue with this, time is getting over. So, we will complete in the next lecture. Thank you very much.